The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, my name is Stuart Carlton and I believe you can hear me now. I am the Healthy Coastal Ecosystems and Social Science Specialist at Texas Sea Grant, and we're happy to present the second in our climate literacy webinar series. And the title of today's talk is Climate Change and the Texas Coast. And today's presenter is Arne Winguth. He's a associate professor at the University of Texas in Arlington. And before that, he worked as an assistant professor at the University of Wisconsin in Madison, and he earned his Ph.D. from the Max Planck Institute for Meteorology in Germany. And we're really excited to have him talk about this topic today. Before I hand the microphone over to him, virtually speaking, I want to just go over a little bit of procedural details. During the talk or the webinar, you're welcome to ask questions. Just chime in. Either if you're on the phone or if you're on your computer, you can speak. You'll need to unmute yourself and just go ahead and ask your question. Then there will also be time at the end for questions. So if it's a bigger picture type thing, feel free to save it for the end. But if there's a point of information or something like that, please feel free to chime in right away. And then secondly, beyond that, if you have this webinar is being recorded and will be available on our YouTube page sometime in the next week or two. And so we'll be able to send that recording out, and feel free to share that link with other people as needed. And I think that is it as far as the preliminary stuff goes. And so I will turn it over to Dr. Winguth from here and make myself disappear. Again, thank you so much.
Okay, thank you very much for the opportunity to give me a presentation about climate change and the Texas coast. So I want to acknowledge the sponsors for this presentation. So this presentation based on a risk assessment of impacts of road due to climate change, and that was supported by the North Texas Council of Government, the UTA Arlington, the Federal Highway Administration, City of Dallas, and the Fort Worth Transit Authority. And then I want to also acknowledge NOAA for the opportunity to do research on changes of the hydrological cycle in North Central Texas, and the National Science Foundation for doing deep time climate, hothouse climate in the past, which gives us also insight for future climate change. So the talk will be based on, I'll give a brief introduction, then talk about the historical climate change and climate variability. And then we'll proceed with a future projection of climate change, also future extreme weather, looking there also in historical perspective, what extreme weather we had in the past, and then address certain impacts discussed in the public, the sea level change due to climate change, the ocean acidification problem, also how does the oxygen concentration in the Gulf of Mexico change due to climate change. And then I will address the issue of how transportation is affected by climate change. So if you're looking on temperature and rainfall, and I picked up here the station of Galveston, I picked up 2011 because that was a year of severe drought in Texas. And you see that while the annual seasonal oscillation of the temperature ranges from the 50s to the 80s, you see that 2011 was a year where temperature even in Galveston were above normal, and so the temperature variation were mostly in the summertime and near to what we recorded in the historical extremes. That is also supported by record temperatures, and on the left side you see the 100 accumulated 100 Fahrenheit days monitored at Dallas-Fort Worth Airport. And then on the right, you see the record of Galveston August temperature. And so what I want to highlight is that the last 2 decades are shown record lengths of hot days, but also extreme temperatures compared to the 100-year record. Now, we see also, which is well known, an increase in the atmospheric CO2 concentration and other gases. So those have been monitored in stations Hawaii, South Pole, and others, supported by by NOAA. And we see also an increase in the global temperature. There's a recent paper by Carl supporting temperature changes of about a 1 degree change since the pre-industrial levels. There's difference in statistical correlations, but this record show actually a long-term trend superimposed on variability, interannual decadal variability in the temperature record. That is also shown if you're looking in Dallas-Fort Worth long-term record. I use that here as a representative for Texas. There's been studies comparing Dallas, the trends of temperature of Dallas and the coast, and so there's a similarity in the trend. So we see, particularly in the summertime, increase in the temperature, and you see also strong signal here due to climate variability like El Nino Southern Oscillation and decadal variation like the Atlantic Mudecadal Oscillation. There's also observations of retreat of ice sheets and glaciers. Here I shown an example, retreat of the Jackson Glacier in the Glacier National Park. I hiked myself up this summer to the Andrew Glacier in the Rocky Mountain National Park, took pictures, and so the size of the glacier is about half the size it was in 2011. We see also increasing trend of sea level. Current increase trend is about 6.5 millimeter per year in sea level, as monitored here, for example, in the Galveston Pier 21. So let me proceed then to the projection, what we see in the future, which is the main topic of this talk. So for the future projection, we rely on climate models. So these climate models are based on fundamental physical law, like the Newton's law of motion, the equation of continuity, conservation of angular momentum, conservation, the first and second law of thermodynamics. So our entire knowledge of physics goes into these models, and the mathematical background has been already set by, for example, Leonhard Euler. These equation has been then extended by NAVIER and Stokes, and so are referred as NAVIER-Stokes equation. We're using same equation in aviation industry and rocket science. So these equations are well established. So what we do is that we then span a grid network over the globe, and the current climate models are typically in a 1 degree horizontal resolution, so 1 by 1 degree, and then the ocean component has 60 vertical layers with a very fine resolution, upper 10 meters. So the upper layers of the ocean are resolved in 10-meter layers. The atmosphere is correspondingly resolved in 60 layers. And so these models, the atmospheric and oceanic models, are then combined and then compute key climate processes like transport, heat exchange, freshwater fluxes, they are solved and numerically solved on supercomputers. We're using them for climate model, one of the fastest computers. One of them is the computer center at Wyoming, the NCSW Computer Center, NCAR Wyoming Supercomputer Center. There are several institutes who carry out climate simulation. My former alma mater, Max Planck, is one of them, then Princeton, the National Center for Atmospheric Research, MIT, and so on, the French group Hadley Center, Japanese groups. And so these models are then compared. And if we run these models with pre-industrial greenhouse gas forcing, we cannot reproduce the current trend in the temperature in North America, Europe, Asia, South America, Africa, and Asia. Only if it includes the greenhouse gas forcing, which are due to anthropogenic CO2 emissions and other greenhouse emissions, then we can reproduce the trend as we observed in the recent decades. So this is ambitious figures, but that shows here the correlation here between the increase of the CO2 emission and then the temperature difference to the historical period 1861 to 1880. And you see that with increasing greenhouse gases in the atmosphere, you see a temperature anomaly. And then the prediction for the future in the business as usual scenario, which is the radiative concentration pathway, where we have a radiative forcing of 8.5 watts per square meter by the end of the century, there we see a global temperature change of about 4.6 degrees Celsius, which is quite remarkable. So if you're looking then in this scenario so we have the different scenarios, the RCP 2.6 scenario, which would be a more sustainable scenario where we would have substantial economic changes adapting to the global warming problem or climate change problem, or the kind of business as usual scenario, the 8.5 scenario. If we are looking on the 8.5 scenario, we see that the Gulf Coast region, Texas, will have an increase in temperature ranging between 4 and 5 degrees Celsius. So 5 degrees correspond to 9 Fahrenheit. I made an example here. So the mean July temperature, for example, for Dallas-Fort Worth, 1900 to 2011, would be 85 Fahrenheit or 29.4 degrees Celsius. And so predicted for July temperature, the mean temperature would be then, and 2100 would be 33.9 degrees Celsius or 93 Fahrenheit. I used one of the model simulation to actually plot it, the extreme temperature here given in terms of Fahrenheit for the Texas coast. On the left, you see January temperature, and then on the right, the July temperature. So the January temperature will, and the Gulf Coast will be 70, which is about almost 10 degrees Fahrenheit higher than the present day. And then you see also the July temperature, which correspond to more extreme values, which we see currently for example, in the Galveston record. Also of interest is the mean change of precipitation. And so in Texas, we have mostly the highest precipitation in spring and fall season. We see a slight increase in the rainfall in the spring season, whereas the fall season appears to be drier. Overall, there will be mixed prediction in the IPCC reports regarding rainfall in the changes in rainfall in the coast. But one important point is that the temperature becomes much higher, and with that, you see a lower soil moisture content, even if you have a higher amount of precipitation. Of course, with the increased precipitation, particularly in springtime, we will see also more flooding. So that leads me to the next part, and so that is extreme weather. And so I will talk there about first how the weather changed. So we see now with the future climate change, we see now a shift to warmer weather. So we would have then fewer cold extreme and more hot extremes. But there's also an indication that the variance of climate shift, so that means more extreme cold and more extreme hot if we do not change the mean. And now we're changing both the mean and the variance, which will lead then to even more hot extreme climate conditions. Examples of severe weather are showing here, for example, tornado watches per year. And so you see here in the Gulf Coast about 6 to 7 tornado watches. That is also the same amount you see it in East Texas. The damages by tornado can be quite severe. I just highlight here, for example, tornadoes here in the neighborhood where you saw in Dallas flying containers, severe damages of homes. So we see probably that, particularly during spring season, there is a higher likelihood that we will have these extreme storms. That has been published by a paper from Diffenborough in the Proceedings of National Academy of Sciences. The other seasons are less clear, less statistically significant, but we see that these extremes and storms will be also seen in the Gulf Coast. An important issue for the Gulf Coast is also the hurricanes. And so we had, in the last decades, we had severe storms like Hurricane Katrina. The city of New Orleans is still in the build-up in response of that hurricane. And then we had Hurricane Ike 2008 hitting the Texas Gulf Coast, and it was just announced in the news that about 80% of the recovery of this hurricane has been completed. So still the Gulf Coast is still resettling from this impact. There have been various studies and support that the hurricanes become stronger. Carrie Emanuel from MIT, for example, in a study published in 2008. And there's also projections for the future where multiple models are intercompared. And so there's a clear signal that the intensity of the hurricanes become higher. There's also a likelihood that the frequency increase, as demonstrated here on the right panel, comparison between modeled hurricane category 4 and 5 present day in the top, and then the lower panel that for 2100. You see also Texas coast will be more affected by these intense hurricanes. We do also studies for the past. Jeff Keel at NCAR, for example, carried out simulations, high-resolution simulations for hothouse climates, and what we see is these superstorms, megastorms, hurricanes evolve in these hothouse climates. Gary Emanuel also investigated the cost of these storms and projected property damage, and so the light gray shaded projection is the projection of accumulated property damage, whereas the dark black shaded graph shows that if we would have a constant climate, we see an exponential increase in the cost. So the increase due to hurricanes is because you have, on the one hand, you have a higher increasing population density on the coast, but then you do have also the effect due to climate change. Now, the next topic, climate change, is a delicate topic because it depends mostly on global factors, how much, for example, Greenland melts, in the next 100 years, and how much Antarctica melt. You can make extreme scenario, which will not happen within the next 100 years. If Greenland melts entirely, we would have a sea level change of about 7 meters. If the West Antarctic ice sheet melts, we would have a sea level change of 6 meters. So projection ranges here with a business as usual scenario from 4 meters to 1 meter, so in the range of about 3 feet by the end of the scenario. On the lower right panel, you see also a recent paper displaying the likelihood of sea level change, which in the extreme would be agreeable with about 5 to 6 feet of sea level. That has been supported also by a study of Ramsdorff, where recent studies showed a range between 3 and 6 feet. So the next topic I want to then continue is the ocean acidification problem. And so since we increasing the CO2 concentration in the atmosphere, so we dissolving calcium carbonate in the ocean. The CO2 eventually invade in the ocean and then dissolve calcium carbonate shells, as shown in the reaction above. So calcium carbonate will be then changing the CO2 and water to bicarbonate. And so that affects the calcification. We see already a historical comparison between cruises sections in the eastern Gulf of Mexico 2007 and then a newer repeat section of 2012. There is a decline in the carbonate ion concentration in the Gulf of Mexico, and so a decrease in the pH value. So that has been published by Vannikov in a recent paper. There's also support from other ocean stations like the Bermuda Atlantic Time Series, Hawaii, and the European STOKES station, which support a decrease in the pH value with the increase of the atmospheric CO2 concentration. Now, future projections suggest with the business as usual scenario that the pH value will be reducing to about 0.4 pH units compared to the historical level. So the Gulf of Mexico is a relatively well-buffered system, so the effects are not as dramatic as in other locations. But ecosystem structures are very sensitive to the pH changes. And on top of that, changes in the temperature, ecosystem and pH value can affect the ecosystem significantly. For example, we have a colleague here at UTA, Lauren Meidlotz, studying diseases in corals with temperature increases, and so there's a significant increase in coral diseases with temperature increase. The next part I want to then point out is the oxygen concentration. And hypoxia has been always a problem in the Gulf of Mexico. This is particularly in the area where in the Mississippi Delta, where we have high amount of nutrients coming into the ocean. So the nutrient increase in nutrient concentration will lead to an increase in the sinking of organic material in the deeper layers, remineralization and decay of oxygen associated with the remineralization. Now, with future climate, we are dealing with two problems: A, changes in the solubility and the biological path. Now, let me talk first about the solubility effect. So a 5-degree warming reduces the solubility in oxygen in seawater about by 10%, and so make it for certain fishes and other organisms, zooplankton, more difficult to live. The other factor is a biological pump, and that is of interest, and for that we need to simulate the biological processes in a global ecosystem model. That has been done in collaboration with the National Center for Atmospheric Research and a group of UC California. Dr. Moore at UC California worked on the ecosystem modeling in the global climate model. Now, this is a student of mine analyzing the oxygen concentration in this global climate model under the RCP 8.5 scenario, and that's shown here, the dissolved oxygen concentration at 200 meters. And so it's interesting, actually, that the oxygen concentration at that level in the Gulf of Mexico appears to be increasing. And so that is linked not due to the solubility. The solubility, with higher temperature, we will have a lower solubility, so it's linked due to productivity changes. And so the productivity changes are linked to higher stratification. We have seen that in past climates, for example, if the ocean becomes more stratified, then the productivity decline. And so we see a decline here in the productivity in the Gulf of Mexico region, which leads then to a reduction, increase in the oxygen concentration at 200 meters. Okay, so finally, I want to then come to the last point, and that is the transportation and effect of climate change on transportation. And so we have studied that in a pilot project in the Dallas-Fort Worth. So I will represent here some of the key results, and that was supported by the Federal Highway Association. So generally, the potential consequences of flooding on roadways is affecting the structural integrity of roads. Then highway and bridges may be affected, particularly by higher stream flow, or if you have flooding by hurricanes, for example, the storm surge may then affect the bridge construction. You have then also erosion of road and bridge supports. You have then disruption of traffic due to the flooding. And there's also higher crash rates, increased congestion, and delay in evacuation and emergency responses. So, for example, the local transport authorities in Fort Worth starting to send out emails to people who are in the area, for example, warning them delay of train service, public transport, or road closures. The National Weather Service starting out sending emergency, so that helps. On the left, the study done in Dallas, rain-related crashes and annual precipitation. So if you see more extreme rainfall in the spring season, so then we will see also higher amount of crashes, and so that has been statistically supported. You see also, of course, if you have in the winter time, that's particularly in North Texas, if you do have then if you have then precipitation falls in form of snow, you have then also higher crash rates with increase of snow accumulation. Hurricanes affect also the infrastructure. We have seen that with Hurricane Katrina and Hurricane Ike. There's an interesting study done from an engineering group looking on the structural number, which represents the overall structural requirement to sustain a certain traffic loading. I mean, decay of a road depends on the amount of road traffic, but also then these environmental impact. And you see that the structure number decreased substantially after the flooding of Hurricane Katrina. You see that the pavement of roads are affected by the flooding. Then I want to also point out the impacts of the higher temperatures. We have pavement rotting. We see more and more roads deteriorating. For example, here in the Dallas-Fort Worth area, a migration of liquid asphalt, road buckling, exploration, uploading pavement and potholes, more frequent lane closures. There's also studies supporting tire deterioration, of course, vehicle engine overheating, exceeding air conditioning, and higher crash rates. There's also higher medical fatalities, for example, by increased rates of heat strokes. So this is a very brief and intense summary here of some of the important factors we see in the Gulf Coast, so impacts due to climate change. There's a significant likelihood that the Gulf Coast will be more often disrupted by future extreme weather events. We see that particularly in the spring, and then in the fall season there will be a higher impact due to hurricanes, more intense hurricanes. The hurricane, due to the increase in the sea surface temperature, the hurricane season increases. The formation of hurricane itself depends on the vertical shear, the sea surface temperature, and then, of course, the Earth's rotation. Coriolis, at the equator, you do not form hurricanes, but you do form them in the Gulf of Mexico. So it depends then mostly in the future what is the shear of the atmospheric flow and the sea surface temperature. And since the sea surface temperature increases, we expect a much longer hurricane season. Then the prolonged heat wave will exceeding that of 2011 in the future. So we will also in Texas have a more severe drought, and with that forest fires during drought conditions. In the Gulf, in the Gulf Coast, you do have enough moisture from the Gulf, so there the danger of fires are not as high as, for example, in North Texas or West Texas. The Gulf of Mexico is generally well buffered, but ocean acidification will be a significant problem for the end of the century. And that is, so ecosystem will be affected not only by the change of the pH values, but by the warmer temperature. And it is mandatory to improve the weather-related monitoring and assessment of damages due to climate change. And so risk studies needs to be done to see which action needs to be done first to minimize the risk due to climate change and severe weather. So this is an overview. Thank you for the attention. I'm ready to take questions now. So you are welcome to ask me any questions. Thank you for the attention.
Thank you very much. And if you do have questions, I think you can go ahead and talk. I will unmute the attendees. Well, yeah, I'll try that. I'll try to unmute you and go ahead and ask a question if you have it. And while we're waiting for that, I actually have a question, Arne. So thinking, let's So you presented a lot of potential effects of climate change coming over the next, the remainder of this century. What do you think, spinning that forward, a lot of the people listening today are work in extension or work in outreach or work directly with stakeholders. What do you think are the types of actions people should be doing, either to mitigate or adapt to climate change? What do you, in your opinion, what is sort of an effective approach to take?
Got there with local stakeholder together. So we highlighted the impact of climate change by 2050 and by 2100. And we also combine then, for example, increase in traffic, or you can also use increase in population on the coast and climate change. And I think this is important to highlight the cost of climate change, assess the cost of climate change, so to make actions to enhance the actions. It's very difficult. Sometimes the topic has been politicized. Also, it's this is a science of climate change. I think these risk assessments, as done by the Federal Highway Administration, are a way forward to address this problem. We need also probably more local weather prediction, improved weather models, downscaling to see then also the local effects in the future. And so that is with the new computing power that is now feasible to do.
Excellent, thank you. And attendees, we were getting some background noise, so if you do have a question, just hit the raise your hand button or type your question in and I will unmute you, because some people were having a little bit of background noise. Okay, great. Well, it looks like there are no additional questions. Again, if something occurs to you, we will be sending out this email or this webinar to our YouTube page, and you can feel free to contact me if you have additional questions or need additional information.
And send me email also and ask me questions by email also. Or can phone me.
Yeah. Well, thank you very much for the presentation, and thank you to the attendees for attending. And we will see you in time for our next webinar. Thank you.
Yeah. Thank you.